Good morning, dear all. This is Jalagam Satheesh Goud, lecturer in physics, TTWRDC, Men Maripeda, Mahapupawad district. Now, today we are dealing with the topic thermodynamics. Thermodynamics means, what is thermodynamics? Thermodynamics is the branch of physics that deals with the relationship between heat and other forms of energy. It also gives the properties of the systems when they are in thermal equilibrium. Now, there is an important and scientist who contributed for the thermodynamics, known as father of thermodynamics, none other than Nicholas Leonard Sadi Carnot. He was born in 1796. He was a French military engineer and physicist. He was known for Carnot cycle, Carnot efficiency, Carnot theorem, and Carnot heat engine. At the age of 27 itself, he published a book, The Reflections on the Motive Power of Fire, in 1824. In that book, he expressed the first successful theory of maximum efficiency of heat engines and laid the foundation of an entirely new discipline, thermodynamics. Now let us know few terminology of thermodynamics. System. A system means a quantity of matter or a region in the space chosen for the study. For example, in our human body, we call digestive system, respiratory system, etc. Surroundings. The mass or region outside the system is called surroundings. And the demarcation between the system and surroundings, that is, system is separated by the surrounding by a boundary. Here you can see in the figure, for example, there is a piston and cylinder. In that, the gas in the cylinder is the system, and cylinder and piston are the boundaries. Outside that is the surrounding, that we can understand from that. Now let us know thermodynamic systems, that is, types of thermodynamic systems. There are mainly three types of thermodynamic systems: open system, closed system, isolated system. Open system. In the open system, heat can be transferred and mass can be transferred. You can take the example of teacup with open lid. You can pour the tea, and even tea can be cooled. Heat will be transferred. Secondly, closed system. Heat can be transferred, but mass cannot be transferred. You can see in the middle diagram, the cup closed with a lid. We cannot pour tea inside, but heat can be transferred. The third one is the isolated system. In this system, neither heat transferred nor mass can be transferred. You can see the thermos flask. Thermodynamic equilibrium. Now, what is thermodynamic equilibrium? Equilibrium means a state of balance. A system is in thermodynamic equilibrium if the following three equilibriums are satisfied. Number 1, thermal equilibrium. Number 2, mechanical equilibrium. Number 3, chemical equilibrium. What is thermal equilibrium? In thermal equilibrium, the temperature of the system is uniform. Then no heat flows. Net flow of heat will be zero. You can see right side, there is the whole system is at 32 degrees centigrade uniformly. Secondly, mechanical equilibrium. In mechanical equilibrium, pressure of the system is uniform. That is, mechanical work done is zero. You can see the pressure is 1 atmosphere all over that system, within the system. Third, chemical equilibrium. Chemical potential of the system is uniform. No chemical reaction takes place in the system. You see, carbon dioxide is there. No, it is not going to any chemical reaction. Other example we will take here. Nitrogen plus hydrogen gives us ammonia. At a particular condition, they are in equilibrium state. They are at particular ratio. So that will be balanced. No change in that ratio. Nitrogen, hydrogen and ammonia, they are fixed. If moves other direction one molecule, the other molecule moves in reverse direction, so that it will be in equilibrium. That how we can understand that. When a system, you see here, when these three equilibriums are satisfied, then only the system is said to be in thermodynamic equilibrium. Now let us understand zeroth law of thermodynamics with the example first. Now consider two cups with coffee in it. Cup A contains hot coffee and the C cup contains hotter coffee in it. Now both are placed in the environment. Then heat is ejected from the cups. Heat is transferred from the cups to the environment, which is at normal temperature. After some time, these two cups come to the temperature of the environment. Now all the three, that is cup A, cup C and the environment B, are at the same temperature. With this, we can say that the systems A and C are in thermal equilibrium with system B separately. Then these two are in thermal equilibrium. That is, then these two are at the same temperature. You see here the definition of the statement of the zeroth law of thermodynamics. If two systems A and B are in thermal equilibrium with a third system, let us say C, separately, then both A and B are in thermal equilibrium with each other. You see in the diagram, the system A, B are separated by insulator, no heat transfers between them. But these two are separately can transfer heat to the system C. Then finally, after some time, the system A and system B are also in thermal equilibrium. Now what it is giving? It gives the concept of temperature. The heat flows till the temperature is the same. So this is the concept of the zeroth law of thermodynamics. Now let us understand work done by a system. Let us take an expression for that. You see, there is a cylinder and piston mechanism. Inside that cylinder, there is a gas. Let us say its pressure be P. Now, due to the pressure, the piston of the cylinder is moved up. The pressure pushes that piston upward direction. Then let us say the piston moves to a displacement delta D. I would like to calculate the work done expression for this. We know the formula for work done is force into displacement. But force is equal to pressure into area. Now substituting their symbols, P into A into delta T is the displacement. Then area into displacement is nothing but volume delta V, change in volume delta V. Then work done can be written as P into delta V. This is the work done by a system. Now let us understand the first law of thermodynamics. The change in internal energy of a system is equal to the heat added to the system minus work done by the system. This is first law of thermodynamics. Here, The left side cylinder piston mechanism is there. Here Q is there with arrow mark. That is, we are giving some heat to that system. Let us say its internal energy be U1. Due to the heat given, inside the gas gets heated. Then piston is moved up due to the pressure developed. Its temperature increases. Then due to increasing temperature of the gas, pressure increases. That pressure pushes the piston upward direction. Then some work is said to be done due to the motion of the piston. Well, then the molecule are also gets heated, the temperature increased, hence internal energy is also increased. Let us say its final internal energy be U2. From this equation, we can understand the amount of heat supplied is utilized to two ways. Number one, to increase its internal energy and to do external work. Hence, Q is equal to delta U or U1 minus U2 plus W. Given in the box, you can see. See, this equation can also be written as delta U is equal to Q minus W. What is the importance of this first law of thermodynamics? It gives the concept of conservation of energy. This we can understand. See here, heat is the energy, internal energy, external work done is the mechanical work done. So these three are equated. Now, what is the sign convention for the first law of thermodynamics? You see, the left side, work done by the system is positive. When the work done by the system, it is taken as positive. Obviously, work done on the system is negative. Heat given to the system is positive. Obviously, the converse, heat rejected by the system is negative. Let us understand this with a simple example. See, system means, let me say myself. When heat means, let us say money. Work means work itself. When I get money, it is positive. When I lose money, let us say negative. Very simple. If I do work somewhere, I will get money, so positive. If work is done at somebody done at me, I have to pay money, then it is a negative. So you can understand this with this way. Now, what are the limitations of this first law of thermodynamics? The first limitation, it does not give the direction of flow of heat. Number two, it does not tell about the extent of convertibility of one form of energy into other. Now, let us understand reversible and irreversible process. In cyclic process, the system is brought to the initial state without any change anywhere in surroundings. That is, cyclic process, what is happening means slowly it is moving, equilibrium with the surroundings, no change in any variable, no pressure changes, neither volume changes, nor pressure changes, nor temperature changes, everything is in equilibrium, but the process continues and reaches the original position after certain cyclic process. But reverse to this, in irreversible process, in cyclic process, the system is brought to the initial state at the cost of some change in the surroundings. Secondly, this process occurs slowly and every stage equilibrium condition is maintained. Whereas in a reversible process, it is rapid and spontaneous, unidirectional, disturbing the equilibrium conditions. Thirdly, third point, this is an ideal concept, that is reversible process, whereas irreversible process is the most practical one. Fourth point, Reversible process is free from dissipative forces like friction, viscosity, electrical resistance, inelasticity, etc. Whereas in a reversible process, it takes place only when there is some dissipative forces. There is a loss of energy. And the fifth point from first law of thermodynamics, that is delta Q is equal to delta U plus delta W equation. Everything is zero. That is, heat given is everything is in equilibrium, hence change will be zero. Every change will become zero. But whereas in a reversible process, we may not give heat, that is, change in heat is zero, work done may be zero, but uh, see here, the heat can be given, change in heat is not equal to zero, work done may be there, it is not equal to zero, but change in internal energy is zero. This we can understand. That is, the temperature condition remains constant. Finally, let us take examples of a reversible process. Here, let us take an ice cream. When it is melted, we get liquid form. When it is solidifies, again we get ice cream. But whereas the spontaneous process, like rusting of iron, natural process, in this case, once the iron rod, iron bolt is rusted, we cannot get back it. So this is an example of irreversible process. Now let us understand Carnot engine, which works in reversible cyclic process. In the left side diagram, the top one is the source of heat, which is at high temperature, T1, called hot reservoir. At the bottom, cold reservoir, which is at lower temperature, T1. In between, there is a working substance that undergoes into cyclic process. See from the top, it goes to the isothermal process, expansion, then adiabatic expansion, then isothermal compression, finally adiabatic compression reaches to the initial position. So for this, if you take a graph, pressure versus volume, you will get isothermal bars are less steeper than adiabatic bars. That is 2, 3 and 4, 1 are isothermal expansion curves, whereas 1, 2 and 3, 4 are adiabatic curves. So this is you learned at intermediate stage. So I think the graph representation, everything you can understand. Carnot engine efficiency. You see, efficiency is defined as the work done to the amount of heat given. If some heat is given, then how much work is done? That is the efficiency. Remaining is some waste is there. For example, if we take food, how much work we have done? That is our efficiency. Some wastage will be there. So that efficiency we want to find. So for that, efficiency eta is equal to W by Q1. That is equal to Q1 minus Q2 by Q1. On simplifying, we get 1 minus Q2 by Q1. But for a cyclic process and a reversible process, Q is equal to MST. M and S are constants, that is mass and specific heats are constants. We can substitute Q2 by Q1 with T2 by T1. This is the known as efficiency of the Carnot engine. So efficiency eta is equal to 1 minus T2 by T1. Now let us understand the second law of thermodynamics with certain examples. You see left side diagram, that is cylinder piston mechanism of any motor vehicle. and a motorbike or car or any other you can take. What is happening in that? You see, there is a fuel. Fuel is injected into the engine. Then, due to the spark produced there, it is burned. Then, the working substance, there it is air, that is gets heated. Then it expands. Due to that expansion, it pushes the cylinder downward direction. Then the cylinder does some work, and remaining heat is rejected as smoke from right side, you can see in the diagram. This is how it works. This process continues in cyclic method. Now the same in block diagram we write in the right side. Here the fuel is burning continuously, so we can take it as hot reservoir. Here the air present on the piston inside the engine is taken as working substance. The piston is moving, doing some work, that is a work done W, and the environment receives the smoke from the engine. By receiving any amount of smoke, the temperature of the environment does not increase. That can be taken as cold reservoir. So you can understand the same with the block diagram as shown in the figure. Now reverse to this, another example we take. There is refrigerator or air conditioners. What happens? The room is at a lower temperature, let us say. Now we give plug-in input. The motor does some work. Then the heat is taken from this room and ejected into the atmosphere, which is at higher temperature. Now we can understand this. The external work is done by the motor to remove heat from the cold room, that is cold room, to the hot environment. See, this is known as heat pump or refrigerator. You can understand here, in the heat pump, heat is taken from the cold reservoir, and for that some external work is done. Then heat is ejected to the hot reservoir. This is in the case of refrigerator. Now in case of heat engine, heat is taken from the hot reservoir. Then the engine does some work W. Remaining heat is ejected to the cold reservoir. Using these two different processes, second law of thermodynamics is defined in two ways. The first one is given by Kelvin and Planck, known as Kelvin-Planck statement. What do they say? They say that it is impossible to convert the total heat taken from the hot reservoir into work, mechanical work, let us say. You see, it is impossible for any system which absorbs heat from a reservoir and converts the heat completely into mechanical work. So this is impossible. The diagram you can see, without ejecting or without rejecting to the cold reservoir, without smoke, on the other hand, we cannot run a mission. The complete heat cannot be utilized to run a mission. This we can understand from this statement. Now second statement you can see, it is impossible for any system to transfer heat energy from a body at lower temperature to a body at a high temperature without external agency. You can see the refrigerator works with the electricity. If electric power or electrical energy is not there, then can we cool that refrigerator by itself? No, never. This is what is Clausius statement. So heat cannot be transferred by itself from a colder body to a hotter body, or from cold reservoir to the hot reservoir. This is what is gaseous statement. Now, in case of heat engine, we calculate efficiency. We have given some amount of heat energy, then how much work is done, then how much heat energy is wasted. That we can understand. Efficiency is defined as the work done by the heat absorbed. Work done by engine by the heat absorbed from hot reservoir, QH. See in the equation, work done is equal to the difference between the two heats. The heat absorbed from the hot reservoir minus heat rejected to the cold reservoir. Then we write QH minus QC by QH. That is equal to 1 minus QC by QH. But for a cyclic reversible engine, QC by QH can be written as TC by TH. So we write the efficiency as 1 minus TC by TH. This is in case of heat engine. Now let us take either in a heat pump or in refrigerator, we define coefficient of performance denoted by alpha. Alpha is equal to the amount of heat absorbed from the cold reservoir for the total work done. That is QC by W. W is equal to QH minus QC. Therefore, we write alpha is equal to QC by QH minus QC. But Q is equal to MST formula we use. Then using that formula, alpha is equal to TC by TH minus TC. This is refrigerator coefficient of performance. How efficient are heat engines? Are they 100% efficient? You see, the answer is no. Why? Because heat is taken to run the, let us say here, in this case, the train is running with the heat, right? Heat produced by burning the coal, or previously, that is steam engines we call. So nowadays diesel is used. No problem. We are using steam engine, let us say. See, in the steam engine, heat is absorbed. That heat absorbed is not completely used to run the train. There is some wastage. Wastage due to friction, and wastage due to released by the heat released by the heat engine, and other forms of energy. Sound energy, any other forms of other energies, light energy and other forms you can take. So this loss of energy is removed to calculate the work done, right, to run the train. So here we can say there is no engine which is 100% efficient engine. The answer is no, right? Now let us understand the concept of entropy. From second law of thermodynamics, we learned the concept of entropy. So actually, we have 4 laws in thermodynamics. The laws of thermodynamics involves certain state functions. The first is zeroth law of thermodynamics. It gives the concept of temperature. First law of thermodynamics, it gives the concept of internal energy. Second law of thermodynamics gives the concept of entropy. Third law of thermodynamics gives the concept of absolute zero, or impossibility to reach absolute zero, right? The coldest temperature, on the other hand, we call. Concept of entropy, let us understand. Entropy is thermal inertia. What is inertia? You see, it is analogous to mass in linear motion. Mass is inertia, we call, in linear motion, and moment of inertia in rotational motion. Entropy does not obey conservation law because it is not cyclic, it is irreversible. It is not reversible. That is why it does not obey conservation law, especially. And we cannot take it back. We can understand more and more about this in the next slides. Now, entropy is the property of a substance. It measures the disorder or randomness of a system. You see, the disorder means with increasing disorder, the entropy increases. For example, in gaseous state, the vapor molecules are more randomly arranged, so its entropy is greater than liquid molecules, than solid. The entropy is also the same manner. The entropy of vapor is greater than entropy of liquid, that is greater than entropy of solid. In Carnot cycle, there is no change of entropy during adiabatic process. If Q1 is the heat absorbed between A and B at T1 and Q2 is the heat absorbed between C and D at T2, then in going from one adiabatic to the other, Q1 by T1 is equal to Q2 by T2, that is equal to constant. That is defined as change in entropy. You see here in the diagram, isothermal curve T1 is there. Here Q1 heat is absorbed and isothermal curve T2 is there. Here Q2 amount of heat is rejected during isothermal compression. See here, in these two cases, there is change in heat. Let us say Q1 and Q2 at constant temperature T1 and T2. Their ratios are same. That is observed. And that gives a constant value, and that is known as entropy, change in entropy delta S. In general, change in entropy is defined as change in heat by constant temperature. Or if it is very point size changes are there, then we take integral form. Integral of ds is equal to integral of dq by t. Now we can define SI unit of this entropy as joule per Kelvin. We know heat is measured in joules, temperature is measured in Kelvin. And other units you can take, heat is measured in calories and temperature in Kelvin. Calorie per Kelvin. This also you can say. Now, a graph drawn between temperature and entropy is known as TS diagram. Already PV diagram is known for us in the Carnot cycle. For the same, we draw the TS diagram. For the steps 1 to 2 in isothermal expansion, temperature is constant in isothermal expansion. So step 1 is at entropy S1, let us say. Step 2 is at entropy S2, say. Then the temperature is constant, hence it is horizontal line. Now from 2 to 3, from step 2 to step 3, what is here? The heat is constant. dq is 0. Then ds will be 0, that is entropy remains constant. Let us say the entropy S2 from step 2 to 3, that is constant. But whereas temperature is changed from T2 to T3, let us say. Here for the step 3 to 4, temperature is constant because it is isothermal compression. So as the temperature is constant, it is again a straight line horizontal to the horizontal, that is to the entropy line, that is temperature remains constant. At the point 4, again from the point 4 to the point 1, there is adiabatic compression. Adiabatic compression, in this case, heat is constant. In adiabatic compression, adiabatic condition, heat is constant. Heat is change in heat is 0. Change in entropy will be 0. Then entropy remains constant. Let us say at S1, the entropy remains constant. 4 to 1 is a straight line and constant with constant entropy S1. So we get a rectangular graph. Now the question comes, what is the use of this TS diagram? It is easy to calculate the efficiency. It is easy to understand the engines the performance of the engines with the TS diagram. Now you see the efficiency with the TS diagram we want to calculate. For that, from the diagram, the amount of heat absorbed from step 1 to 2 is equal to area under that graph to the entropy curve. Then we get T1 is the constant temperature, and S2 minus S1 is the that is change in entropy. The product is like you can say length into breadth. The product is like length into breadth. The T1 is upward direction, that is the highest temperature at the point 1, that is length, and S2 minus S1 is the breadth. Length into breadth is the area. That is how you can understand this. Similarly, the amount of heat rejected from step 3 to 4 is the area under 3 to 4 curve. That is equal to, let us say the temperature is T2 here, T2 into S2 minus S1. Now, heat energy converted into work is equal to heat absorbed minus heat rejected. Total heat absorbed by the substance and the work is done, remaining heat is rejected to the sink. Here the work done means the difference between these two energies, that is heat absorbed minus heat rejected. Substituting the above values and taking common, we get T1 minus T2 into S2 minus S1. This is the work done. Now, our interest is to calculate efficiency. Efficiency is equal to heat energy converted into work by amount of heat absorbed. So, eta is equal to T1 minus T2 into S2 minus S1 divided by T1 into S2 minus S1. Cancelling the entropy differences in the numerator and denominator, we get eta is equal to T1 minus T2 by T1. On simplifying, we get eta is equal to 1 minus T2 by T1. This is the efficiency we calculated from TS diagram for the working substance of a Carnot engine. Now, what is the change in entropy in reversible process? At BSc standard, usually we are getting these questions in semester examinations also. Usually there are entrance point of view conceptual questions are based on this. You have to understand them clearly. Here, what is the change in entropy in reversible process that we wanted to find? Sometimes the question will be there. Show that the change in entropy in reversible process is zero. Zero. How? So for that we are taking Carnot engine and the graph we are taking Carnot diagram. Consider Carnot cycle with a reversible process. In a reversible process, from PV diagram for its working substance, we are calculating change in entropy in each case. Say during isothermal expansion from step A to B, the gain in entropy will be it absorbs Q1 heat at temperature T1, hence Q1 by T1. During adiabatic expansion, change in entropy from B to C is 0 because the change in heat is 0. Right? This you can understand. Right? Now, from the point C to D, you see here, C to D, it rejects heat Q2 at temperature T2. Hence, there is a loss of entropy, that is Q2 by T2. Now, the fourth and final step from D to A, is there any change in entropy? The answer is no, because there is no change in the heat, hence no change in the entropy. Now, summing all these, we get there is a net gain in entropy of working substance in the whole cyclic process, that is Q1 by T1 minus Q2 by T2. Here, Q1 by T1 is the um, what is that? Gain in entropy. Q2 by T2 is the loss in entropy. But in complete reversible Carnot cycle, we know that Q1 by T1 is equal to Q2 by T2, that is equal to constant. Hence, Q1 by T1 minus Q2 by T2 must be equal to 0. Therefore, the change in entropy in reversible process is 0. This we can understand from this derivation. It's very conceptual, you can understand. So, you can generalize that the change in entropy in any reversible process is 0. Remember well. Now you see, does entropy increases? The answer is yes. How? In all factories, smoke is given out. In all motor vehicles, smoke is given out. What happened to that heat ejected, heat released to the environment? That increases disorder, that increases entropy. Right? This we can understand from this diagram. Now, how much increase will be there in a reversible process? That we wanted to find. All natural processes are irreversible process. We learned this already in the differences. For that, consider an irreversible engine performs a cyclic process. Let us take working substance absorbs Q1 heat at a temperature T1, at a high temperature T1 from a source, and let it rejects heat Q2 at a lower temperature T2 of the sink. So that is Q1 heat is absorbed, Q2 heat is rejected. Then what is the efficiency? Efficiency formula we know that 1 minus Q2 by Q1. 1 minus Q2 by Q1. That is in case of reversible or irreversible. But in case of reversible engine, the formula is 1 minus T2 by T1. According to Carnot's theorem, the efficiency of reversible engine is always greater, or irreversible engines is lesser efficient. Therefore, we can write the efficiency of irreversible engine 1 minus Q2 by Q1 must be less than the efficiency of the reversible engine 1 minus T2 by T1. On simplification, we can write, that is cancelling 1 and 1 both sides, and minus and minus both sides, the less than symbol will be reversed, right? When multiplied both sides by minus, the values are deferred. So then here Q2 by T2 is greater than Q1 by T1. Then we write Q2 by T2 minus Q1 by T1 must be greater than 0. Here Q2 by T2 is the gain in entropy by the sink, and Q1 by T1 is the loss in entropy by the source. Source loses that much entropy and sink gains this much entropy. Hence, there is a change in entropy and the system increases in the irreversible process, the physical quantity called entropy. That is, the entropy of a system increases in the irreversible process. Now we discussed that the entropy of any irreversible process increases, but all natural processes are irreversible. Then what about universe? Universe is always in nature, it is a nature, it is under natural process. So definitely its entropy is increasing, that is its disorder is increasing. Now let us understand this with the Big Bang theory. See, when the Big Bang is there, that is the initial time, let us say, during the first seconds there are the minute particles like quarks are there, goddess particles we are saying. After 10 to the power of minus 17 seconds, we found those things. We don't know about during the time duration between 10 to the power of minus 17 seconds. After that, about 3 minutes, there is a formation of nucleus, formation of atoms taken place. After about 3 million years, there is a formation of microorganisms like virus, bacteria, etc. After about 1 million years, there is a formation of galaxy, that is stars, galaxies, planets, everything are formed in that. Galaxy contains number of stars. Each star contains number of planets. All these put together one galaxy. Such galaxies are formed. Now, at present, we are about 14 billion years after the Big Bang formation. Now, human beings are evolved. Many animals, plants are evolved and more scattered. So, this is how the disorder is increasing. That is, the entropy is increasing in the universe. See, dear students, this is how we can understand the entropy. Now, to learn anything, sky is your limit. You can learn more and more with this small ignition. Thanking you. Bye.